So, hello everyone. My name is Martin Aguiar. I'm a researcher at the University of Beira Interior. I work for the LITecS laboratory. Oh, okay. Sorry. I work for the LITecS laboratory, which is the Laboratory for Innovation and Technology for Sustainability. And we are developing work on how can we 3D print sensors. But why do we want to do this? First of all, we are working within the Robot Sudway project, and this project aims to help small and medium enterprises to be more competitive by helping them with robotics, with automation, with digitalization, and we develop robotic systems, adaptive grippers. We work a lot with soft gripping technology. We use multimodal perception and AI-based strategies. So, how do you do this? First of all, we start with the design. We design the grippers. We simulate the grippers for 3D printing. We do experimental analysis, and then we implement them in robotic systems, and we try them, we test them, and we implement them in the industry. How do we do this? With computer vision for robotic manipulation. We detect the fruits, in this case, using AI, and then we can sort them according to the client's needs. But robotic handling has a big problem, which is for soft products, if we do not have a soft gripper, it can create damage on the fruits. And this is damage right after gripping. After a few hours, it starts browning, it starts decaying, it degrades the product, and it can even become a health and safety risk. This can be a problem, and how can we solve this? We have two ways of solving this problem. By designing a gripper or using a commercial soft gripper that is not hard on the surface of the fruit, and these grippers, they are available commercially. They can be quite expensive, so this is a problem for small and medium enterprises. And what we do is we design, and we are developing a tool that designs the soft gripper specifically for the product we are manipulating according to the required parameters. And there is another way that is measuring the pressure we are exerting on this fruit. Perfectly, we can have both. We can have a soft gripper that is sensorized to measure the pressure it is exerting on the fruit's surface. So if we have a soft gripper, we are designing the soft gripper. We have published work on the design of the soft gripper, although it is using the fin-ray effect, which is a known effect. We have some modifications to the design, and we can just embed a force sensor. This sensor would allow us to measure the force it is exerting, or the pressure, if you want to be specific. And this way, we can measure when to stop gripping and when to start handling the product and avoid the damage this way. But if we have a gripper that we have on the market, but we want to print it, we would also like to print a sensor. The question is it possible? And to answer the question, first, you must understand how does it work? How does a resistive force sensor work? It works by having a conductive circuit, a flexible membrane, a conductive ink, and I won't bother you with the details, but when we apply force, the conductive circuit contacts the conductive ink, and then we have a variable resistance on the sensor overall. But can we fully 3D print a sensor? That is the question we want to ask here. And if so, with which technology can we use? Can we use a low-cost technology, affordable for small and medium enterprises, or do we need to use a very expensive technology that we have seen here, certainly in the fair along your visit? Well, we were thinking about it, and we looked at the shelf, and we had a spool of conductive filament from Recrius, and we started thinking, perhaps we've tested this filament for circuits, but it is very resistive, so perhaps we can try to make a sensor out of it. And why would you think this? A conductive filament is a composite material that is composed of a non-conductive polymer, in this case TPU, and conductive particles. And these conductive particles, if you push them together or you stretch them apart, they will change the resistivity of the material. Also, you have another factor, because this is a material with a positive Poisson's ratio. If you stretch the material, although the length of the material increases and the section area decreases. What this means is that we are changing all the parameters in the resistive sensor that we are building. So with deformation, we change everything, so the resistance is expected to change. Well, and we tested this. We we put a sample on a strain testing setup, and you can see here the sample we used. This is standard testing, and we started characterizing resistance versus displacement. This is the sample Luan over there was doing for his master's thesis. He was testing a lot of these samples and measuring the results. And what we saw is very interesting, because not only we get a resistance change with displacement, but we also get a difference in the behavior according to the direction we are printing the sample. So if we are printing along the sample, it has a different resistance and a different behavior than if we are printing against the sample. So we can change the resistivity not only using the material, but also using the design. Next, what we did was print a Finray effect gripper designed for conductive material, and we started testing it using this. In this case, it's just using a multimeter, but then what we did was apply it on a soft gripper testing setup. We did cycle testing. We measured the electrical resistance of this material over time, and we also used a difference force sensor to compare the data, and then we managed to find a relation that Rodrigo presented yesterday. If you would like to know more about this, I'd be very glad to show you, and Rodrigo would also be very glad to show you. We have a demo set up for this fair, so if you want to see this working, you can ask us afterwards and we'll show you. But this is not the focus of the presentation today. So what I'm going to show you is what else can we do with these sensors. So we started thinking. We have a material that we can print that changes properties according to deformation. What kind of sensors can we build with this? So to understand how can we change, we first need to understand what we want to change, what we want to sense, and the principles and behaviors behind the underlying principles behind this. So what I'm going to try to show you live today, and hopefully, okay, is I'll use a multimeter to measure the resistance of different samples so that we can see how they change with different conditions. So what can we sense? First, we start with deformation. We have a small sample here, a small sensor, that I'll just plug here on the multimeter. And you can see here that when I bend this sensor, see how much it changes. It can change quite significantly. What this means is that we can use this as a sensing device for bending, for twisting, and I'll use this sample for stretching. You can see if I'm not moving, it changes very slightly because I'm moving a little bit, but if I stretch it, it changes a lot, quite significantly for a sensor, okay? What else can we sense? We can do a touch sensor, resistive touch sensor. You can see here, if I touch the sensor, it changes again by a lot. And even a pressure sensor, I use a non-resistive medium to press the sensor, and you can see how much it changes when I apply some pressure. Of course, these are sensors that we've been developing, like fast development. They are not very, very, very developed. This is very early stage development. Oh, I forgot to show you humidity. Perhaps the sensor is not cold enough to accumulate humidity, but you can see it also changes. If I blow on it, humidity leaves the sensor and conditions also change. Well, what else can we do with this? I already showed you a lot of applications, but the sky is the limit, right? And when having my head in the sky, remember that my PhD was about frost detection sensors, and I thought, why not do a frost detection sensor to try and measure frost on heat exchangers? So what I did was develop a small sensor. This I'll show you. This is the sensor. It is very compact, very small. It has 2 electrodes and a gap. It measures the difference in resistance of the material that is the medium material between electrodes, and it is designed for additive manufacturing. What this means is I have a 3D printer, has a nozzle width, so I use this nozzle width for the channels so that it can build everything in one pass. It is better to build with a composite, a flexible material that is not very easy to print. It is multi-material, so that this part here on the bottom insulates it from the heat exchanger. And then what we did was print it and test it on the heat exchanger. First of all, another property that is interesting on these materials is because it is a very thin sensor and because the TPU is a good conductor of heat, considering it is a polymer, we always manage to have frost on its surface. Believe it or not, it's not very easy on these kinds of sensors to have frost built on their surface unless they are good conductors of heat. It is easy to install, and then when we tested it, we actually got good results. This is not easy to understand, so I'll help you interpret it. This curve in here, the orange one, is a computer vision system that we use for frost detection. So this is actually the amount of frost that was building up on the heat exchanger. And this curve here is the sensor curve. So what this means is we actually managed to detect frost in this region. So on the beginning, we detect an amount of frost, but then the sensor saturates due to its design. We can improve the design to increase the amount of frost it can detect. So we have a detection in here. We have here a small detection that is not visible by the camera, but is condensation happening on the surface of the frost sensor. And here is when we start a defrosting operation. We remove the frost. When we heat the frost, it melts, it accumulates on the sensor, decreases its resistivity. And then when we dry the heat exchanger, this is all the things that we cannot detect with a camera, but we can detect with a sensor here, which is very interesting for us. And we detect when to start or when to stop a defrosting operation. This avoids us extra energy and helps with refrigeration system efficiency. Something else that made us think when looking at it, we could understand this part, this part, this part, this part, but we had trouble detecting this part right here because it has a slope. It means the sensor resistivity is slowly increasing when frost is accumulating. But this is not due to frost accumulation because, as I told you before, the sensor has saturated right about here. So what could this be? We try to check the sensor measurements against all the other sensors because we have our setup rigged with humidity sensors, temperature sensors, and so on. And what we found out was a strong relation between sensor measurements and temperature measurements. So what this means is that this sensor can also be used to measure temperature changes. This must be always a thing we have to consider when using a medium that can change with different parameters. Because in this case, it changes with frost, it changes with humidity, it changes with temperature. So in the circuit design, in the sensor design, we must consider what can affect this sensor reading and how can we distinguish what we want to measure from noise caused from other parameters. And I'll show you, unfortunately, I do not have a portable frost creating device here, but what I have is a system to create heat that is portable. You're probably familiar with it. So you can see that it changes with temperature. It goes up the resistivity with high temperature, and it decreases with low temperatures, which is something we expect to find in semiconductors and these sort of materials, as opposed to metals. And this is what we can do. Hopefully, I'll try to show you the last part, which is a mini game we made. Perhaps I'll have the same trouble we had yesterday. Here it is. So what we did was we built a remote, and we have a small game, and we use this joystick here to move the Pac-Man's blind cousin. Don't mind, he does not have an eye. We press the B button to make a target appear on the screen, and when it touches the target and we press the A button, sorry, it has to be moving. OK. Technical problems of live demos. So what we can do here is, what we want to show you here is that we can simply, out of the printer, make sensors that work and that we can use to control. It can be Pac-Man, it can be any other application. What we believe is that in the future, you'll be able to print something in a household 3D printer that comes out of the printer. You plug your microcontroller into it, you code it, and the circuit is already built in, the sensors are already built in, and this is just a proof of concept, but it can be a first step to a greater 3D printer future. And if you want to test this remote afterwards, I'll gladly let you. So to finish my presentation, I'll have to get Pac-Man out of the screen. Okay. What can we take from this? Conductive flexible filaments are usually thought as something to make a circuit, but is perhaps even a better approach to think of it as a way to make a sensor. Okay. The versatility of these systems, of these sensors, is something we have to consider always when designing the sensor, because, as I told you, when I'm measuring frost, I might not want to have the interference of temperature, of humidity, of any other sort of factor of deformation on the sensor. So everything has to be considered and has to be during the design phase. We have made sensors for compression, tension, flexion, torsion, pressure, temperature, humidity, frost. All of these sensors are, of course, resistive sensors, which means that we can measure them with a simple voltage divider. And all the results I showed you today require further investigation. Of course, this is very early stage. Some of the sensors that are in this presentation today are something that came up while we were analyzing results, such as the temperature sensor. And we want to characterize this better. So what are we working now? We are developing research on these sensors. We are trying to understand how they behave, all the phenomena that affect their changing parameters. We are trying to find a method to calibrate them, to standardize them, so that we can also establish partnerships with filament companies to optimize the filament for the production of sensors, and then create a library of 3D printable sensors that we can then allow everybody to use and tune and open source it, so that we can all work together in the development of these 3D printable sensors. So thank you very much. I think I still have time for a few questions. And thank you for your time.
Thank you very much. Fascinating stuff. Yeah, there's some parts here you can come and have a play with, especially the gripper as well from yesterday. Come and ask any questions that you have for Martin, because that is the last presentation of the day. So thank you very much. Somebody has to be last, and I always appreciate it. So thank you.